All right, let's dive into one of the most wonderfully strange ideas in all of mathematics. The idea that there isn't just one infinity, but a whole tower of them, each one bigger than the last in a way that's almost impossible to imagine. We're going to see just how deep this rabbit hole really goes.
So here's our game plan. We'll start with the really old puzzle that totally stumped people for ages. Then we'll see how a completely new way of thinking about size turned that puzzle into a super powerful tool. We're going to use it to count things that seem, well, uncountable. Witness a proof that is just pure genius, and we'll end up right at the very edge of what math can even tell us.
For most of human history, infinity wasn't really treated like a number. It was more of a philosophical problem. It was just this process that never ended, and anytime someone tried to pin it down and treat it like a single thing, all of logic just seemed to fall apart.
And that leads us to the big question for today. Your gut feeling probably says, yeah, of course, infinity is, well, it's infinity. How can there be different sizes? But what if that gut feeling, that intuition, is just completely wrong? What if we could actually prove some infinities are bigger than others?
So this is the paradox that really messed with people's heads for centuries. Galileo pointed out that you can pair up every single whole number with its perfect square. So 1 goes with 1, 2 goes with 4, 3 with 9, and you can do that forever. But this felt so wrong. How can a part of a set, the perfect squares, be the same size as the whole set, all the numbers? It seemed like a total contradiction, a sign that we should just leave infinity alone.
But then along comes this mathematician in the late 1800s, Georg Cantor, and he has this totally brilliant idea. He looks at Galileo's paradox and says, wait a minute, what if that's not a paradox? What if that's the definition? What if that perfect pairing is exactly what it means for two infinite sets to be the same size?
Cantor gave this idea a name, cardinality. He said, forget trying to count to infinity. It's impossible. The new rule is way simpler. If you have two groups of things and you can perfectly pair them up one to one with nothing left over, then those two groups have the same size. It's like checking if everyone at a dance has a partner. If they do, you know you have the same number of leaders and followers without counting anyone.
Now, the fancy math term for this perfect pairing is a bijective function, but really, just think of it as the ultimate matchmaking for numbers. If you can find a rule that creates that perfect one-to-one pairing, then the sets have the same cardinality. That's it. Case closed.
So this right here is the critical jump we have to make. We have to completely let go of our everyday intuition. In Cantor's new world, that old obvious rule that a part has to be smaller than the whole gets thrown right out the window. The new rule, the only rule that matters, is if you can pair them up, they're the same size. And that one shift changes everything.
So armed with this brand new superpower, Cantor basically went on a hunt. He started testing all kinds of different infinite sets to see if this pairing idea held up. He really wanted to find out, is there any kind of infinity out there that's actually bigger than the good old counting numbers?
And the results he found were just wild. I mean, sure, the even numbers could be paired up, that's easy, but then he showed that all the integers, positive, negative, and 0, could also be put in a one-to-one list. But the real shocker? The rational numbers, all the fractions. Now think about this. Between any two fractions, like 1/2 and 1/3, you can find an infinite number of other fractions. They seem infinitely packed in, totally dense, and yet Cantor proved they are the exact same size of infinity as the simple counting numbers.
And this is how he did it. It's just so clever. He laid out all the possible fractions in this giant infinite grid. At first glance, it looks like there's no way you could ever list them all out. But Cantor found a path. By just snaking his way diagonally through the grid, he created a single path that is guaranteed to eventually hit every single fraction. He turned a 2D infinity into a 1D list.
This discovery set the baseline for infinity. He called it Aleph null, or Aleph 0. It's the size of any set that you can, at least in theory, line up and count. And the takeaway here is just mind-blowing. Our intuition about how dense or crowded a set of numbers is has absolutely nothing to do with its actual infinite size.
Okay, so up to this point, every infinity Cantor looked at turned out to be the same size, Aleph 0. But he had one more suspect, the real numbers. All the numbers, including the irrational ones like pi or the square root of 2, the ones with decimal expansions that go on forever without repeating. To tackle these, he was going to need his greatest weapon, the diagonal proof.
The logic behind this is just beautiful. It's a proof by contradiction, which is a really cool kind of logical trap. First, we're going to pretend that we can do the impossible, that we can actually make a complete, infinite list of every single real number. Then, we're going to use that very list against itself to build a new number that by its very design can't possibly be on it. And if we can do that, it means our starting assumption was just plain wrong.
So let's imagine this is it. Here's our supposedly complete list of every real number between 0 and 1, stretching on forever down the page. Now the genius here is to ignore almost all of it. We're only going to pay attention to the digits that run down this one diagonal.
Okay, now we build our new number. Let's call it D. And the rule for building it is incredibly simple. We look at the very first digit on the diagonal, and we make the first digit of our new number different. Then we look at the second digit on the diagonal, and make our second digit different. We just keep doing that, all the way down the line forever.
And here it comes, the knockout punch. Think about this number D that we just built. Could it be the first number on our complete list? No way, because we specifically made its first digit different. Could it be the second number on the list? Nope, we made its second digit different. No matter which number you pick from that list, our new number D is guaranteed to be different from it in at least one place. We've used the list to create a number that cannot be on the list. The conclusion is inescapable. The list was never complete. It can't be. The real numbers are uncountable.
Now this proof did way more than just settle a question. It completely shattered our old ideas about infinity. Proving that the real numbers were uncountable meant that, yes, there is definitely a bigger kind of infinity out there. And that, it turns out, was just the start.
So here we have it, in black and white. The size of the counting numbers, which we call Aleph 0, is strictly, provably smaller than the size of the real numbers, which we call the continuum. We found a bigger infinity.
But Cantor wasn't done. He then came up with what you call an infinity engine. It's a theorem that says for any set you can think of, you can always make a new, bigger set just by gathering up all the possible subgroups or teams you can make from its members. This collection is called the power set, and it is always a bigger size of infinity. This creates an endless ladder of infinities. There is no biggest one. For any infinity you can possibly name, you can use this trick to find an even bigger one.
This, of course, led to a brand new, burning question. Okay, we know Aleph 0 is the first rung on the ladder of infinity. And we know the continuum, the size of the real numbers, is on a higher rung. But is it the very next one? Or could there be other, intermediate infinities lurking in between?
This question got a fancy name, the Continuum Hypothesis. It was considered so fundamental that in 1900 it was named the single most important problem for mathematicians to solve. And the answer they finally found, decades later, might be the strangest thing in all of math. The question is unanswerable. Using the standard rules of mathematics, you can't prove it's true and you can't prove it's false. It's independent of our system of logic.
And this really shows the incredible power of Cantor's original diagonal idea. It wasn't just about counting numbers. The exact same core logic, using a system to construct something that defies that very system, was later used by Kurt Gödel to show the inherent limits of mathematical proof, and by Alan Turing to show that some computer programs can never be proven to work. It's like a master key for finding the absolute boundaries of what we can know.
Which leaves us here with a choice. We can literally choose to build our mathematical universe on a foundation where no infinities exist between the whole numbers and the real numbers. Or we could choose a foundation where they do exist. And both universes are perfectly logically consistent. So the final question is, if we get to choose our truths at this fundamental level, what does that tell us about the nature of mathematical truth itself? Is it something we discover or something we create?